Good morning, my students. So, how are you today? Are you feeling well? And I hope you all guys in healthy and energized to study today. So, before we dive into our physics session, let's open this class with a prayer. Maybe Yolanda can lead us into the prayer. Okay, thank you, Yolanda, for leading us in the prayer. So, students, before we dive in into the slide, I have one to challenge your mind with a quick question. There is a two question that I want to ask to you. Number one is why does it feel much hotter inside a car parked under the sun with the window closet uh, rather than we when we outside from the car. Number two, it's when if the earth has its own natural blanket of gas, why is that blanket now becoming a problem? To answer that, we have three learning objectives. Number one is we're gonna talk about explore the physics behind global warming from solar energy. Number two, we were gonna talk about wave frequency to radiative forcing and climate solution. And the last, we will understand why our planet energy system is out of balance. So, welcome to our topic. It's unraveling the physics of global warming. So let's take a look at the first slide. First, we need to realize that not all light is visible. Energy travels in a wave of different frequencies. Our eyes can only see visible light, but universe is full of invisible waves. In physics, understanding the difference between shortwave and long-wave radiation is the key to understanding how Earth heats up and why it stays warm. Now, what's come from the sun? It's a short-wave solar radiation. The sun emits high-energy short-wavelength radiation. It includes the ultraviolet and visible light. This wave have a high frequencies and easily pass through Earth atmosphere to warm the surface. So because the waves are so small and high in energy, letting them slide right in. But what happens when the Earth wants to bounce that energy back? It changes into the long wave infrared. That's number two. Earth will re-emit energy as long wavelength as long wavelength infrared or heat radiation. So this low frequency wave carry less energy and are easily absorbed and trapped by greenhouse gases in the atmosphere. But Miss, why do they behave differently? So let's take a look at the number three. It's about energy and frequency. They have when higher frequency, it's meaning shorter wavelength. That's mean more energy per photon. The solar radiation penetrates the atmosphere easily. So while infrared heat is trapped, a critical difference driving a global warming. So you can guys think of it's like a fast, tiny arrow that can pass through a net easily. But when that can pass through the net easily, but when the teeny arrow that bounces back, it turns into the big, slow beach ball that gets stuck into the net. So for the whole picture, uh, let's let's check about this spectrum. The electromagnetic spectrum ranges from high-energy gamma rays to low-energy radio waves. Visible light and ultraviolet sit near the high energy end. Infrared sits just below visible light and invisible to our eyes but felt as heat. So when you guys feel warm near a campfire or under the sun, you actually feeling that invisible infrared wave. So let's go deeper. What is shortwave solar radiation? The sun emits energy in the form of electromagnetic wave because the sun is extremely hot, around like 5500 degrees Celsius. It releases mostly shortwave radiation, including visible light and ultraviolet rays. So look at the massive number. It's like 5500 degrees Celsius. It's like super hot, right? Shortwave radiation has a high frequency and high energy, allowing it to travel like 150 million kilometers through space and pass through Earth's atmosphere with a very little absorption. Earth surface and understanding its properties in the first step unraveling the physics of global warming. So let's trace how the energy arrives in the next slide. The sun constantly radiates energy outward in all directions. A teeny fraction of the energy, but an enormous amount travel like 150 million kilometers to reach us. This incoming solar radiation is short-wave energy. Visible light, including visible light, ultraviolet rays, and near infrared. This short wavelength pass easily through our atmosphere, like light through a glass window. When the sunlight hits Earth's surface, land, ocean, also forest, it is absorbed and converted into the heat. The ground and ocean warm up, storing this energy. Like Miss said before, think of Earth like a sponge soaking up sunlight every single second of every day. So now what happened to all that stored energy? Here's the question. Here's the answer to the next slide. It's about Earth radiate. Once the Earth's surface absorbs incoming solar energy, it warms up and every warm object emits radiation. But here's the key difference. The Earth doesn't emit shortwave radiation like the sun do. Why? Because the Earth is much cooler than the sun. It emits long-wave infrared radiation, essentially heat energy invisible to our eyes but detectable as warmth. This governed by Wien displacement law. When cooler objects emit at longer wavelength, this law have a strict rule in physics. When lower temperature, it means longer wavelength. So think of this way. When the sun blasts in high energy, the short wave light, Earth responds with a low energy, long wave heat. This difference in wavelength is the heart of greenhouse effect. Why the atmosphere treats incoming and outgoing radiation very differently. So remember, energy in mass equally energy for a stable climate. When the balance is disrupted, it means the temperature will rise. So now let's we take a look to the gases behind the greenhouse effect. Greenhouse gases trap infrared radiation and re-emit it back to the Earth, warming our planet. So let's take a look at them. I will explain it one by one. First, there is a carbon dioxide, or we can call it CO2. CO2 absorbs outgoing long-wave infrared radiation and re-emits in all directions, including back toward Earth. And so this is the scary fact about the CO2. When burning fossil fuels has raised CO2 level from 280 parts per million to over 420 parts per million. It's like since the industrial revolution, it's like a big jump from 200 to 400. Second, the greenhouse gases trapped in the earth, it's methane or CH4. Methane is 80 times more potent than CO2. So over 20 years at trapping heat, it absorbs infrared specific wavelength band, acting like a thick thermal blanket. Source including livestock, landfills, and natural gas leak. So the third is nitrous oxide or N2O. So N2O is released from fertilizers and combustion. It persists in the atmosphere for over like 100 years and nearly 300 times more effective than carbon dioxide per molecule. It's a small but still powerful contributor. And last is water vapor. Water vapor is the most abundant greenhouse gas and act like as a feedback amplifier. So when the earth warms, more water evaporates and trapping even more heat, accelerating the warming cycle already set in motion by carbon dioxide. So water vapor and carbon dioxide, it's like a chain reaction. So to make this explain about the greenhouse effect, I want to connect this is to the like I mentioned it before about the car analogy. So here's the car analogy about greenhouse effect. Number one, about sunlight enter. Shortwave solar radiation so easily passes through car glass window, just just like a passes through Earth atmosphere. Sorry for the notification. So the glass is transparent to this high energy. Uh, The glass is transparent to this high energy, short wavelength, so this is allowing sunlight to flood the interior. So the second is heat builds up. When the car seats and the dashboard is absorbed sunlight and re-emit energy as long wave infrared radiation. So this lower energy wave cannot escape through the glass easily. So the heat from the sun is can go out from the car. So the heat is trapped into the inside the car. So this lower energy wave cannot escape through the glass as easily. So the interior temperature rises rapidly. Like I said before, the heat inside the car is raised. The number three is about glass trap the heat. Just like the greenhouse gases in our atmosphere, the car glasses blocks outgoing infrared radiation. So when energy is trapped inside, it's driving temperature higher. So we can tell this is like a perfect real world model of the greenhouse effect in uh, our daily life. So I want to make sure you all guys understand. This is bring us to our final concept about radiative forcing and energy imbalance. In simple terms, radiative forcing, it meaning a measure the difference between incoming solar energy and outgoing infrared energy when this balance tip Earth either warms or cool. So we can explore the three key ideas behind this energy imbalance. Number one, it's about incoming solar energy. The sun emits short wave radiation. Uh, so when the sun emits short wave radiation can pass through the atmosphere and heat of Earth's surface. On average, Earth absorbs about like 240 watts per square meter of solar energy. This is our energy income. So this is what we get for free from the sun heat every day. Number two, it's outgoing infrared energy. When Earth re-emits energy as long-wave infrared radiation back toward the space, greenhouse gases absorb this outgoing radiation, reducing energy loss and trapping heat within the atmosphere. So this is reduce our spending or energy loss. So this is the last. It's about positive forcing. When positive forcing, it's meaning warming. So when incoming energy exceeded outgoing energy, the forcing is positive, causing warming. Rising carbon dioxide level have increased Earth radiative forcing by plus 0.7 plus 2.7 watts per square meter. It's science pre-industrial times. Because why can that happen? Because it's a plus sign. So that means our planet is getting warmer and getting warmer year after year. So according to the slide, how many watts per square meter does Earth absorb as its solar energy income? As like I said before, is like 240 watts per square meter. Okay, that's all for today. I want to make this wrap things up for our final slide. So what's next? Climate mitigation is in your hand. Reducing emission through energy like renewable energy, energy efficiency, also energy efficiency, also and smarter choices and can slow radiative forcing. So for every action switching to clean energy, reducing waste, also advocating for change is help Earth to restore Earth energy balance. So you guys can may do that three things that I said before, like the clean energy, reducing waste, and advocating change to make our Earth it's for a better place. So that's all for our class today. Congratulations for you all guys to your excitement for today class. I will send your homework in our group chat in our group class, so you can fill out the homework, and don't forget to give it back into the next week. So thank you for being such an awesome class today. So see you next week and have a wonderful day.